What is this? A weird symbol is floating here. I feel like I've seen it somewhere before.
Be careful, you shouldn't touch it. So this is today's problem.
Is that so?
This symbol certainly resembles something we know. Yes, it's differentiation.
What, really? Oh, now I remember seeing such a symbol. I had almost forgotten about it.
To solve this mystery, we'd probably need to review the definition of differentiation first. If you already know the definition of differentiation, please skip to 116. Now let's assume there's a graph of y equals f of x on a plane. Then take 2 points on the graph. Let the x-coordinate of one point be x. And let the x-coordinate of the other point be x plus h. The slope of the line passing through these 2 points is...
I already got it! The change in the x direction is x plus h minus x. And the change in the y direction is f of x plus h minus f of x. So, this gives the slope of the line.
Well done! In the denominator, x and minus x cancel each other out. In the end, only h remains. For this slope of the line, taking the limit as h approaches 0, we're calculating the slope of the tangent line at x. This is called the derivative of f of x. Differentiating f of x means finding its derivative.
I'm starting to remember now.
Now if we extract the numerator of the fraction representing the slope of the line, it looks like this. And actually this expression can be represented using delta h. This delta h is called a forward difference, a type of a finite difference. It represents the change in f corresponding to the change in x by h. Now can you figure out what delta hx would be?
You mean to consider the case where f of x equals x? Then, f of x plus h simply becomes x plus h. And f of x becomes x, so the answer is h. Well, if you move x by h, the change in x is h. It's pretty obvious.
Thanks, Sundaman. With this in mind, let's try calculating this expression.
It kind of looks like a derivative.
I intentionally wrote it to look like a derivative, just like the symbol in the problem. The numerator has delta h alone, but let's consider it as being applied to f of x.
Which means, the numerator represents the change in f. The denominator represents the change in x, which is simply h itself. Oh, this is the slope of the line.
That's exactly what it is. In other words, this is the step before differentiation. It's like the derivative, but before letting h approach 0. If differentiation is a continuous concept, differences can be considered a discretization of differentiation. When h is sufficiently close to 0, it becomes an approximation of differentiation. So then, if you'll let me slightly abuse the notation, intuitively it feels like this.
I see. As h approaches 0, the discrete version of d by dx becomes d by dx in the true sense. This is kind of fascinating.
This is literally the process of finding the slope of a tangent line.
But looking at the problem's symbol, I don't see h in delta h anywhere.
Oh no! I completely forgot about it.
Maybe you're a little tired today?
Thanks for worrying, but I'm fine. Indeed, when we use differences to represent the slope of a line, we represent the change in x with h. Here let's fix h to 1, and write delta 1 simply as delta.
Why are we treating 1 as special?
That's a great question. First, when h equals 1, the denominator becomes 1. So the formula takes a very simple form.
You're right! Differentiation seems so complicated, but discretizing it makes it this simple.
Also, this difference formula is not just a discrete form of differentiation, but is actually well known in another form. Here the change interval is 1, so we can restrict x to natural numbers or integers. Specifically, if we restrict x to natural numbers, this corresponds to the definition of a sequence of differences. By taking the difference between two consecutive terms in a given sequence, a new sequence is generated. This is called a sequence of differences.
Oh, this is what I learned in class.
When we simply say difference, we often consider cases where h equals 1. Now, let's actually calculate a difference. But before that, I'd like you to recall this formula.
When you differentiate x to the n, the result is n times x to the n minus 1. Oh, right, there was such a formula.
Let's try doing the same thing using differences. First, try calculating this expression.
This is the difference of x squared? Since the change in x is set to 1 right now, first add 1 to x. then subtract the original expression.
You're right.
Expanding x plus 1 squared gives this, and the x squared terms cancel out, so the result is 2x plus 1.
That's kind of an interesting result. Let's compare this with differentiation. The derivative of x squared is 2x, but the difference of x squared is 2x plus 1.
Now that you mention it, what exactly is this plus 1?
We need a bit more information. Let's calculate the case of x cubed as well.
Got it. Now the derivative of x cubed, let's calculate its difference. Just like before, first add 1 to x, then subtract the original expression. Expanding x plus 1 cubed gives this, and the x cubed terms cancel out, but a lot of terms are left.
This result is more complicated than before. When you differentiate x cubed, it becomes 3x squared, but its difference turned out like this.
It doesn't feel very clear. Huh? I have a bad feeling about this.
Be careful, a hint is coming.
Is that what it is? Whoa, this is...
This is falling power.
Huh? Do you know it?
No, I'm just reading it out loud. Never mind that, look at this. X to the second falling power means that instead of multiplying x by itself, the second x is reduced by 1. And x to the third falling power is, instead of multiplying x 3 times, the second x is reduced by 1, and the third x is reduced by 2.
I see. Falling powers are very similar to regular powers, but like factorials, the values descend by 1 each time. But if this is the hint, what does it mean?
Maybe if we take the difference of it, we'll find something.
Huh? Really? It should have explained it all the way. Well, fine. Let's calculate the difference of x to the third falling power. First, take the expression with x increased by 1, and subtract the original expression. What do we do from here?
X to the third falling power looks like this.
Oh right. Unlike x cubed, the values decrease by 1 each time. So the x plus 1 to the third falling power is... It starts at x plus 1 and decreases by 1 each time. First multiply by x, then multiply by x minus 1. Now what do we do?
Other common factors?
That's it. These parts are definitely common factors. If we factor them out, first it looks like this, then it becomes like this. Here the x terms cancel out, so the answer is like this.
You're only saying like this. By the way, if you look closely at this part,
This is x to the second falling power.
this is an interesting result. When you calculate the difference of x to the third falling power, the result includes x to the second falling power. In general, when you calculate the difference of x to the nth falling power, the result can be expressed using x to the n-1 falling power like this. The proof can be done in the same way as before, so let's leave it to readers.
Well, it's not readers, it's our viewers, but anyway, this is a fascinating formula. It corresponds exactly to the formula for the derivative of x to the n.
In the world of differences, falling powers play the same role as powers do in the world of differentiation. It's such a mysterious relationship. Let's look at one more important example.
E to the x remains unchanged when differentiated. This is another well-known formula. So what happens if we take the difference instead of the derivative? The difference of e to the x is e to the x plus 1 minus e to the x. Then, factoring out e to the x, first it becomes this, and then it becomes this.
It seems the coefficient e-1 has appeared.
What could this be? Maybe it's better not to use e in differences.
What happens if we replace e with 2?
Oh, that sounds like a good idea. Then let's calculate the difference of 2 to the x instead of e to the x. This time subtract 2 to the x from 2 to the x plus 1. Then factor out 2 to the x. First it becomes this, and then it becomes this. This time the coefficient becomes 1, so the answer is 2 to the x.
What a beautiful result.
Just as e to the x remains unchanged when differentiated, 2 to the x remains unchanged when the difference is taken.
In the world of differences, 2 plays the same role as e in the world of differentiation. This is another mysterious relationship.
Huh? What's this?
It seems there's a calculation problem prepared for the end.
Since sigma's being used, a and x seem to be integers here. It looks complicated, but let's give it a try. Okay, let's take the difference. First increase x by 1, then subtract the original expression. Next expand each sigma. In the first sigma, t moves from a to x. Thus it can be expanded like this. In the second sigma, t moves from a to x minus 1. So it can be expanded like this. Since we're subtracting, most of the terms cancel out, leaving only f of x.
We've seen this result somewhere before.
Does it?
When you take the sigma and then take the difference, the result returns to f of x. There is a very similar formula in calculus.
Could it be?
Yes, the formula known as the fundamental theorem has the same form. To be precise, it's called the first fundamental theorem of calculus, which states that integrating and then differentiating brings you back to the original function. However, note that in the world of differentiation, t and x are continuous, whereas in the world of differences, they are discrete.
In other words, just as derivatives correspond to differences, integrals correspond to summations.
That seems to be the case. Differences not only approximate derivatives, but they are also a fascinating topic by themselves.
It's fascinating that even in the discrete world, structures similar to calculus exist without limits.
Well then everyone, take care.
See you again.